Soutrik and I am acting as a TA for this NPTEL course, namely Learning and Adaptive Control, or Nonlinear and Adaptive Control. And this is a live discussion session which would be happening every Friday from 6 p.m. to 8 p.m. in the evening, Indian Standard Time. So without any further ado, let's take some questions. So Ashima had a question, right? Am I spelling your name correctly? So can you explain briefly the Lipschitz continuity? Okay. So in order to do so, let me share my screen. I am a little bit ill today, so pardon my voice. It may get better in the next week and so on. So I hope you can see my screen. And if you can see my screen, please give me a holler. Can you see my screen?
Yes.
Okay. So let's look at Lipschitz theorem. So Lipschitz continuity is a kind of continuity which is generally dealt with in nonlinear systems and nonlinear control. So suppose you have a normal function which is fx is equal to x square, right? So the Lipschitz continuity says that given 2 points, let's say x1 and x2, the function of x1 minus function of x2, the norm of it is less than some constant times norm of x1 minus x2. Now, this is a very vague statement, and to demystify it a little bit, uh, let's uh, let's look at some intuition behind this. So if you graph the function of x square over here, so it would look like this. So herein lies x, and herein lies fx, right? Now, if you look at 2 points over here, let's say here and here, the theorem is saying that the slope is bounded by some constant k. In other words, if I look at 2 points x1 and x2, if I compute the slope between them, so let me make this a different color. So if you join the 2 points over here, and I magnify it over here, let's say. So this is your function, and this was the point connecting them. These two are the like, this is essentially this slope is essentially norm of fx1. So let me write it over here. It is essentially norm of fx1 minus fx2 divided by norm of x1 minus x2. And the norm is essentially the distance between these two for the scalar case. So this is the slope of this line, this red line over here. And according to this theorem, it is saying that the slope is bounded by positive k. So regardless, if this slope is in the negative direction, let's say I have this kind of structure, and the line connecting was like this, the slope, the absolute value of the slope would be less than k. So in essence, if you look at this point over here, the function must lie in this cone. which is plus k slope and minus k slope, the function, whatever the value of the future function may be, must lie between this region, this conic region, and similarly over here as well. So the function must lie in this region, these two regions of the cone. Now, the beautiful thing about this Lipschitz continuity is that it like subsumes the continuity and the differentiability properties. So if you look at the this function must be differentiable at each point, and this function must be continuous at each point, right? So the Lipschitz continuity is the bigger brother of these two. I hope that answers your question. So let me go to that. Ashima, did it answer your question? Okay, nice. So does anyone else have a question that we can tackle now? Yes, come again. I can't hear you.
So while taking the Lyapunov function,
Yeah,
when we
there is an echo in your voice. Could you come again, please?
consider the boundaries of the Lyapunov function.
Uh, can I explain the Lyapunov function?
No, sir. We generally take sometimes only single Lyapunov function. Sometimes we are taking the boundaries of the Lyapunov function. So when we need to take the boundaries,
As in boundaries, as in I couldn't understand the question. Boundaries of the Lyapunov function in what sense?
means it is bounded between the two different values. Suppose
Right,
uh, v of x is equal to suppose, x square means it is in between v of 0.5 into x square to 2 times
right,
x square.
right. So v of x is x square in your example, and v of x must be is like bounded by 0.5 x square and let's say 3x square, right? Is this your question, right?
Yes,
So when are we considering these bounds, right?
yes, sir. Yes, sir. That is my question.
Okay, okay. So to give you a brief understanding of why we do this, we have to first understand the intuition behind the Lyapunov function, right? So the intuition, I hope this has been covered in the class as well, but still for completeness sake, I'm helping you understand this. So the intuition is essentially uh, any object, if its energy is slowly decreasing over time, it would be acting a little bit stable. What I mean by that is, suppose you have this kind of hill, let's say. I have a car over here, a car or object, anything over here, and I'm trying to roll this ball or car, whatever, down this valley, right? So I'm rolling this car down this valley. So at each point of time, the potential energy or whatever uh, of this ball is decreasing, right? As we go along this direction, due to the gravity, the potential energy of this ball is decreasing at each time step. So if you look at the potential energy at, let's say, t is equal to 0, that was greater than potential energy of t is equal to some 10 seconds from now, right? So in 10 seconds of time, you have less potential energy than your predecessor, right? So what happens as time progresses, the system loses energy. The system loses energy and it essentially moves into this kind of stable state. So this point at the bottom of the valley is known as the equilibrium point. This is a very crude example. This is just meant to be acting as an like analogy or an intuition behind this Lyapunov function. So this bottom point in the valley is known as the equilibrium point. And if you reverse this valley as well, so if you have this kind of structure of mountain and you are pushing this ball up this valley, pushing this ball up this valley to this point, at the brief point of time where when it is over here, it is stable. It's not stable in the sense that if I nudge it a little bit, it would roll down the valley, it would roll down the mountain. But if given no force, if I stand over here, I would stay there, right? So this is also an equilibrium point. So these kind of positions where I have no external force, and if there is no external force, I stay there. It's known as an equilibrium point. Now, Lyapunov function is just like is equivalent. I'm not saying like exactly equal. It's equivalent to an energy-like function. So this energy-like function is useful in understanding how nonlinear or dynamical systems are stable or unstable and how we can design controllers to make them stable. So if you look at, let's say, x dot is equal to minus x. So where x is a scalar value. So is this system stable? What would be the answer? Can anyone answer? You can use your mic. So I have no restrictions over here.
For our system under consideration, it is a cubic function. So stable only, sir, stable only.
Okay. So when I ask this stability question, the first question in your mind must be stable about where, right? So I hadn't mentioned that point. So
Equilibrium
yeah,
point.
about the equilibrium point. Now, what is the equilibrium point in this system?
Origin, sir.
Origin. How did you say that?
We make the differentiation of x dot is equal to 0 by x is equal to 0 minus x is equal to 0.
Right, right. So x dot must be equal to 0. This implies minus x must be equal to 0. And in other words, x must be equal to 0. This is an equilibrium point, right? Okay. So given this equilibrium point, we can comment on the stability of this system. Now, if you look at the dx by dt is equal to minus x, you can solve this integration by from t naught to time t from x naught to x. This is essentially, I can shift this t over here, sorry, minus over here, and this is essentially natural log of x naught to x is equal to minus t minus t naught. Okay. Now if I consider this over here, this is ln x divided by x naught is equal to minus t naught bracket, and thus x of t is essentially x t naught multiplied by e to the power minus t naught. Right. Now if you look at any point in this situation, if I start from x t naught here, x naught over here, it would decay down to 0 exponentially. It won't hit 0 like it would hit 0 at infinity. It won't hit 0 before that, but it is going down to 0 exponentially. So if I perturb this uh, point from this origin, it would still decay down to 0. So this is one way of looking at the stability, and this is very like crude way of doing things, because for some complex system like x dot is equal to some like sine of x plus 3 cos x plus some like tan hyperbolic anything, like very complex systems, this kind of integration is very difficult to compute. So what Lyapunov theory gives us is this like intuitive idea that decreasing the energy along the system trajectories makes sure that the equilibrium point is stable. So the Lyapunov function is generally denoted by this v of x. Here state, uh, there are many kinds of Lyapunov function. So currently I'm considering that the Lyapunov function is only varying with this state x and not time t or any other variable. So this is state dependent Lyapunov function. So state dependent Lyapunov functions are like, let's say it can be half of x square, or it can be 1/4 of x to the power 4. Why these powers of 2 I have considered, it would be clear a little bit later. So let me go through that and then do it. So if I give you this Lyapunov function, suppose I give you this Lyapunov function over here. So this is the Lyapunov function over here. So you can take that Lyapunov function and you can differentiate it with respect to time. It would be x into x dot, and it is x substituting this dynamics over here, this dynamics over here, it is minus x square. Now the properties of Lyapunov function must be so that this function is positive definite. Now what we mean by positive definiteness of a function, and this would tie beautifully to that boundedness thing that you asked. Positive definiteness of a function is implies that that function is always greater than 0 for all x in the domain minus the origin. What I mean by that is that the energy cannot be 0 or less than 0 at all points of the state space except the origin, and the function must be identically equal to 0 at origin. Okay, so this is known as a positive definite function, and similarly you can write negative definiteness. Negative definiteness implies that v of x is less than 0 for all x in this domain minus this origin, and v of x is equal to 0 for x equal to 0. And similarly, there is this concept of semi-definiteness. Semi-definiteness implies one is positive semi-definite and one is negative semi-definite. So positive semi-definite is the same thing. I just copy and paste this over here. But this can be equal to 0. And negative definiteness is the same thing. Sorry, negative semi-definiteness is the same thing when this is equal to 0. So what you asked is this boundedness thing, right? So v of x is less than, greater than or equal to 0.5 x square, and this is less than or equal to 3 x square. So this part of the equation, this part of the inequality, is saying that this is positive definite. How? Because this is positive definite. And how you comment this? You see that this is this function over here, 0.5 x square, is always greater than 0 for all x in real number without the origin. Right? Do you see this?
Yes.
Yeah. So
Yes.
if a function is always greater than a positive definite function, this is also a positive definite function. Right? And the second condition, this condition, is called decrescence. Right? Now, decrescence doesn't come into picture willy-nilly, because decrescence is applied when it is time dependent. The Lyapunov function is time dependent, but you can comment on decrescence even when this is state dependent. It would be identically equal to like the Lyapunov function itself. So for proving decrescence in the state dependent case, state dependent Lyapunov function, this function can be equal to directly v of x. So that condition holds, or any constant, positive constant greater than like k greater than 1. So let me explain this decrescence a little bit, which is a little bit confusing, but fear not, it is very like intuitive enough. So have you understood this positive definiteness, the left hand side of this equation?
Sir, this 0.5 into x square is less than v of x, means our v of x is always greater than 0.5 into, like yeah, we have to view this one like this, or v of x is greater than 0.
Yeah, so the thing is that this is easier to say when this is state dependent. The problem arises when where there is a time dependence in the Lyapunov function. So if you look at this, let me create a Lyapunov function which is now, is this positive definite or negative definite or whatever? What is the definiteness of this function? How can you say this? Any answers? Actually, I can't see your chat, so if it would be helpful if you turn on your mic and speak. Anyone? So herein lies the beauty of this kind of thing. So this kind of thing, some alpha 1 of x and some alpha 2 of x. So herein lies this beauty of this kind of structure. So if you look at this function, if you look at this function, t is always greater than or equal to 0. Am I correct? Time cannot be negative in this structure. So if you, for t greater than or equal to 0, if you plot this function that is over here, e to the power minus t and t, this goes from 1 and asymptotically to 0. Am I correct? Am I? Is it okay, right? You can see my screen and everything, right? Hello.
Yes, sir. Yes, sir.
Yeah. So this value always like e to the power minus t varies between 0 and 1. It is not technically equal to 0, but it's, yeah, 0 and 1, right? So the subtraction e to the power minus t is between 0 and minus 1. And you can add 2 in the on the both sides, so it would be 1. Is this okay? I'm just simply performing basic inequality manipulation, right? So when you subtract, like you multiply the inequalities by a negative quantity, the inequalities reverse. So if you look at, let's say, 3 less than 5, if I multiply minus 1 on both sides, if I multiply minus 1 on both sides, this becomes minus 3 is greater than minus 5. Is it okay? So when I have this inequality over here, if I subtract minus 1 on all sides, the inequalities get flipped. So it is essentially like this: 0. Okay. If you don't understand, please feel free to stop me at any time. I can answer your questions. Are there any questions up to here?
No,
Okay.
sir.
Okay. Now you understand how this is coming, right? You understand how this is coming. Now what we can do is we can multiply x square on all sides. We have x square less than 2 minus e to the power minus t x square and 2x square. Is this okay? Like I have performed very simple manipulations, right? So this is okay, right? Now if you look at the original Lyapunov function, which was over here, I can write is it okay? Now, we couldn't comment on the positive definiteness of this function, right? Because this was very hard to compute. T was also varying and the function was also varying with x, right? So for each time t, there could have been some cases of time t where this could have been negative or this could have been positive. We couldn't say for sure. This is a very simple example on e to the power minus t, but suppose you have some complex function on t multiplied by x square or something, right? This can be negative or can be positive. You can't say for sure, right? But if you look at this function is not dependent on t at all. And this function is also not dependent on t at all, right? But this function is, right? So for all time t, for all time t, this inequality is holding, right? Now, if you look at this function, left hand side function, this is positive definite. And if you look at this right hand side function, it is also positive definite function on x, right? Am I correct or not? Yeah, it seems I have lost you guys. So till where have you understood? So could you point me to there? I could re-explain that if you want. Anyone?
Yes, understood.
Which part? Come again? I couldn't hear you. Your voice is very much like laggy. So could you type it out? I can read it in this chat. Could you type it out? The person who was saying. Okay. Okay. So you have understood up till here, right? So this is less than a positive definite function on x, and it is greater than, sorry, greater than a positive definite function on x and less than a positive definite function on x. Is that so? Right. So the left hand side, we just focus on the left hand side for now. This function being greater than some positive definite function on simply x implies that this function v of x is positive definite. So this is the definition of positive definiteness for time varying Lyapunov functions. So for state dependent Lyapunov functions, this was very easy to see because you plug in different values of x and you look at that the function is not becoming less than 0, right? But for different values of t, you can't comment on the positive definiteness very like in a trivial fashion. So what you need to do is you have to find a positive definite function on x which is less than this function. Am I making sense?
So can you repeat that again?
Right. So given this example, this was very difficult to find whether this is positive definite or not. So suppose you have a different value of ft and x square. Let's say this is your Lyapunov function, which is dependent on this, right? So you can't comment whether this v of x t is greater than 0 for all x in domain D minus this thing, minus origin. You have to also ensure that it is holding for all time t is greater than or equal to 0. Right? So this is a very difficult condition to satisfy. But if you can show that v of x comma t is greater than some alpha 1 of x, where alpha 1 of x is positive definite for all time t, then this is also positive definite. I mean, this is very like simple to observe, because if this is greater than 0, then this which is greater than that quantity is also greater than 0. Am I correct?
Yes, sir.
Okay. So the left hand part of this bound you have understood. So this is nothing but the positive definiteness quantity in like in simple terms, right? Now let me show you a trick what we do. So consider this time, this is your state, and this is the function v of x comma t, right? So since I can't draw in 3D like very good, so you have to bear with me. So suppose there is a Lyapunov function which is like this initially, and after time progresses, it is like acting kind of like like this. It's moving like this, and it's moving like this, and so on. Right. So this, if you look at the time, like if you uh, stack different Lyapunov function values like along the x-axis, this kind of thing can be visualized, right? You need like good visualization skills to like see this in action. But suppose this kind of Lyapunov function exists, right? The essence of this entire bound over here is saying that if you look at this curve, there exists two envelopes, one like this and one like this, between which the Lyapunov function lies at all time instant t. So if you have this two tubes like this and you extend them into the time, right? The Lyapunov function would always lie in this region. Is this okay? In other words, the Lyapunov function, the basic Lyapunov function, cannot be going too below this positive definite function, and it cannot be going too bigger than this Lyapunov function. So the below condition is known as the positive definiteness condition, and the above condition is the decrescence condition. So the decrescence, or this this upper bound, is required when this time derivative, not time derivative, but this Lyapunov function is time dependent, and you need to perform uniformity analysis. Now there is this concept of uniformity in this. Uniformity. Uh, Wait, just give me 1 second. Yeah, I'm back. So the stability result or whatever result you are trying to derive using Lyapunov analysis for non-autonomous systems. So autonomous systems were the systems where the time derivative of state was dependent only on the state and not on the function time t, right? So this was autonomous. And for non-autonomous, x dot was equal to f of x comma t. So this kind of autonomous systems are always uniform. So there is no uniformity, like need to mention uniformity for autonomous systems. For non-autonomous systems, there may be such that, so uniformity implies that given an initial time t naught, let's say, suppose you start the system at, let's say, 1 second, and you start the system at, let's say, 10 seconds, the uniformity criteria says that if it is stable at 1 second, starting from 1 second, it must be stable starting from 10 seconds as well. So there is this like problem in non-autonomous systems that there may be some time instance where the if you start the system from that time, the system may be unstable. So in order to prevent that, we need to show that our stability results are uniform in nature, right? So if you look at the uniformity theorem in the Lyapunov theorem for the uniformity, time dependent functions, there is this concept of decrescence of the Lyapunov function. So decrescence is nothing but the Lyapunov function must be less than some positive definite function on x only. Is that clear? I know I have like given you very heavy words as of now, but they have been covered in the class. And if there is any doubt in this autonomous and non-autonomous system, I would be happy to clear it out. So give me whatever you got. Is this clear?
Yes, sir.
So you now see why the lower bound and upper bound are there for non-autonomous systems, and why they aren't specified technically in the autonomous systems is because suppose you have this function v of x. Now the assumption is that it is always greater than or equal to 0. Yeah, sorry, greater than 0, right? So this is the positive definiteness assumption on the Lyapunov function, right? So if it is not dependent on time t, you can find two functions which are like this. So you can find two functions, and those are essentially exactly v of x. So any Lyapunov function which is positive definite, mind you, is itself positive definite and decrescent, right? So there is no need to mention this like boundedness in the Lyapunov functions which don't depend on time. But if you depend on time, then you must have this boundedness, right? So there are two cases there as well. So if you don't want to show uniformity, then you just have to show that there exists a function alpha 1 which is less than v of xt. But if you want to make your result a bit better, uniformity, then you have to show that there exists a Lyapunov function. So this condition must always hold. The left hand side condition must always hold. But if you want to show a better result, which is uniformity result, you have to have a Lyapunov function which is decrescent. Is this clear now? Okay.
Sir,
So
can you see again uniformity case?
which one?
Just above, just now you have told, no? Can you elaborate this?
This
So
uniformity thing, this over here?
yes, sir. Yes.
Okay. So uniform result. So give me 2 seconds. Yeah, I am back. So this had been covered in your class, which is non-autonomous systems. So I sense that there is a lot of confusion on non-autonomous systems. So let me cover it a little bit, if that's okay with you, right? And this is probably the hardest topic of Lyapunov analysis, non-autonomous systems, right? So sir may have covered this system, very simple system, which is x by t plus 1. Did sir mention this system anywhere? A simple yes or no would suffice.
No, sir.
No, okay. So let's figure out what this is stable or not. So to first figure out what is stability along this, uh, we have to figure out what is the equilibrium point. So what is this equilibrium point? This is very easy question. So go ahead.
0, sir. X is equal to 0.
X is equal to 0, right? X is equal to 0. How do you compute that? So you take this right hand side function, which is dependent on t as well, and you equate it to 0. Now for all time t, f x t is equal to 0 implies that x is equal to 0. Now this is not always the case, right? So if you look at this system, x dot is equal to x minus t, what is the equilibrium point on this?
It would be time dependent.
There is a time dependence of the equilibrium point, right? So there is no equilibrium point in the system, because equilibrium point by its definition must be time independent. There exists a point in the state space at which the derivatives or the system trajectories, the derivative of the system trajectories must be equal to 0 for all time t. So there is no equilibrium point for this system, right? Now, if you look at this system, the equilibrium point was at 0, and it is completely time independent. So equilibrium point was at 0. Now, given this equilibrium point, we have to comment whether this equilibrium point is stable, uniformly stable, or what. Right? So we have to figure out whether this is stable or not. So there is Lyapunov function v of x comma t. Let's say this is x squared. Right. So this is a candidate Lyapunov function. Why candidate? Because I have not yet tested the time derivative of this. I have just proposed this Lyapunov function. So there can be any number of Lyapunov functions which you can propose, right? So here, if you look at this, Lyapunov function is time dependent, but there is no time over here. You can create a Lyapunov function which is static in time. This is completely up to you. You can also have this t of x square, which is time dependent, right? So t into x square. So you have to see whether this is positive definite or not, and it is decrescent or not, right? So let's say if I consider this t into x square, this is very like interesting looking, right? So can I find a positive definite function alpha 1 of x which is less than x comma t? Can I find this? Give me any function.
Yes, sir. Yes, sir.
What is that?
You can we can add some constant point in between 0 to 1.
Now this must hold for all t. Suppose t is equal to 0. What would be the value of this v of x comma 0?
0, sir.
0. Suppose I have v of x comma t is equal to 1. What is this value?
X square, sir.
Right. Some constant k. This would be kx square. Right?
X square. Yes.
Now, for any value of t, there is one lower bound always. What is that? This is very interesting question. So do you want the answer? The answer is 0. Every function for every time instant t is always greater than or equal to 0. Right? And now this function 0 is also a function, right? Is positive definite? Technically it's positive semi-definite. Positive semi-definite, right?
Yes, sir.
So this is not a valid Lyapunov function for this problem, because this must be positive definite and not positive semi-definite. the lower bound must be positive definite and not some positive semi-definite. So this Lyapunov function over here doesn't work. So what can work? So let's say I have this v of x comma t. So let me write this, that this doesn't work. Does okay? Is it clear why not? So yeah, now let's modify that Lyapunov function a little bit. So t plus 1 x square. Now is this a valid Lyapunov function? So let's see what it is. So t plus 1 is always greater than 1 for all t greater than 0. Is this correct? Very simple algebra. So I can multiply a positive quantity on both sides because x square is a positive quantity. I can multiply it on both sides. So t plus 1 x square is greater than x square for all t is in r plus, right? So let me rearrange this. So t plus 1 of x square, which was nothing but your v of xt, is greater than x square. You can't comment on the upper bound. Can you comment on the upper bound? What happens if t is infinity? Then v of x comma t is infinity at t is equal to infinity. So there is no upper bound for this Lyapunov function. Only a lower bound exists, right? So this function is at best positive definite. You can't say it is decrescent. Right? So this is a positive definite candidate Lyapunov function. It's not a Lyapunov function yet. So it has not yet received its privileges as a Lyapunov function, but it is a candidate Lyapunov function. Is this okay?
Yes, sir.
Correct.
Okay.
Yes, sir.
Now, how does this Lyapunov function become, this candidate becomes a proper Lyapunov function? So there needs to be a second test which must be done on this. And that test is the derivative test. Must be equal to less than or equal to 0. So this is the second test. Right? So let's compute the derivative. So you have this v dot. So it is t plus 1 into x, इसका derivative. So d by dt of this is essentially, so you have to apply product rule over here. So it would be x. So it was x square, not x. So it would be x square plus t plus 1 into 2x into x dot. Is this correct?
Sir.
Yes or no? Yes?
Yes, sir.
Okay. Now if we substitute that original dynamics over here, so this was your original dynamics. I'm placing it over here. Now, can we cancel this t plus 1 and t plus 1 from the numerator and denominator? What is the condition? That t plus 1 must not be equal to 0, right? So can this t plus 1 be equal to 0? No, right? Because time is always positive. T is always greater than or equal to 0. So this cannot be equal to 0. Hence, we can simply cancel these two terms out. And we obtain minus x squared, right? Now, the derivative, time derivative of bx comma t is equal to minus x squared, which is essentially, we can also write less than or equal to, because it is equal to, right? This is essentially minus alpha 3 of x, where alpha 3 is positive definite, right? X square is positive definite, right? So minus of x square is negative definite. So this is essentially a negative definite function. So let's see what all conditions have been satisfied. So first is that v of x comma t was greater than or equal to some alpha 1 of x for all time in real positive, and alpha 1 was positive definite, right? The second, v of x comma t, the derivative of it was less than or equal to minus alpha 3 of x for all time in real number, and alpha 3 was positive definite. In other words, the Lyapunov function is an energy like function because it is positive definite, and along the time, like as time progresses, the energy is decreasing because the derivative is negative. So the energy is decreasing and it is an energy like function. So in other words, the origin or the equilibrium point is stable. Here I have not mentioned uniform stable. Why haven't I mentioned that? Because the original Lyapunov function, the candidate Lyapunov function, was not decrescent. If this was decrescent and you had proved that this is like negative definite, then this could have been uniform stable. And this is even better than stable. It is asymptotically stable because this is negative definite and not negative semi-definite. Negative definiteness gives a one step higher result, which is asymptotic stable. Right? Now, the like this key part of the puzzle is missing, the uniformity, right? We cannot say from this Lyapunov function, that this is uniform or not. Right? You can say that this is asymptotic stable. That's very good. That's well and good, right? But you can't say that it is uniform stable. Right? To show a uniform stability, you had to construct a Lyapunov function, candidate Lyapunov function, which was decrescent, and this condition was satisfied that v dot is less than some negative definite. Sorry, less than negative. It is negative definite. Right? So am I clear? Did this example help a little bit? Hello.
Yes, sir.
So I hope this resolves that question. This was a very long answer to that simple question, but I hope that it is helpful to you all. So can we move to the next question, if there are any?
Sir, can you show some L2 union L infinity space? Some insights into. Can you show some insights into L2 union L infinity space?
Right. Okay. Cool. So let's look at what are L2 functions and what are L infinity functions. So let me test you a little bit. So what are L2 functions? What is the definition of L2 functions? And what is the definition of L infinity functions? So let me test you a bit. So what are L2 functions? Anyone?
Integral of square root of integral of square of a function.
Square root of
Square root of integral of square of a function.
integral of square of a function. Let's say I have this function, some f of t, square of function dt. What are the integral bounds?
0 to t.
T. Or is it t or is it something else? Infinity. Now, what is this? I mean, this is a like expression. So how does this say that this is function is L infinity, L2 or not? There's a key component missing in this definition. What is that? It's very simple. You are just missing a key piece.
Absolute value of f of x.
No, that is the definition. So absolute value, the square of absolute value is the square itself. So that doesn't matter. So this is known as the norm, to norm of a function, right? Now L2 function means that this norm is less than infinity. In other words, this quantity is less than infinity implies that it is finite, right? And similarly, the L infinity thing is 0 to infinity, absolute value of fx, sorry, not fx, ft dt must be less than infinity. This is the infinity norm, of a function. And this is the to norm of a function. Do you have understanding on the norms? Norms of a vector, norms of a matrix. Look, no, I'm not focusing on matrix now. Do you have any idea of what is norm? I had initially commented on norm over here. I forgot to tell you what is norm. Do you know about norm, or should I give you an understanding as well? So for completeness sake, let me do that. So let's take a slight detour on norm. What is norm? Hello, am I audible now?
Yes, sir. Yes, sir. Audible, but
So I got disconnected a little bit. So where were we? Norms, right? Till what point did you catch me? So this could you hear, right? So this definitions could you hear, right?
yes, sir.
Okay, cool. So let me give you a brief of norms of a vector, let's say, right? So in scalar case, let's say you have some variable x, right, which is scalar. So it's a real number, right? So what do you mean by absolute value of x? Could someone define it mathematically? So everyone knows what is absolute value of x, but can you define it mathematically?
If x is positive, positive value. If it is negative, we need to make the sign opposite.
What? Not else, otherwise. This is your
Like
absolute value, right?
Yes, sir. Yes, sir.
Now, can you say what is an absolute value of a vector? It's very counterintuitive to think that, but can you say what is a like what is the magnitude of a vector, let's say, or an absolute value of a vector? Can you say? You have heard about this in coordinate geometry. I can give you a hint.
That would be L2 norm.
Yeah, so L2 is a very mathematical
is
way
it
of
like the
saying that.
Euclidean distance you're talking?
Exactly, Euclidean distance or distance, right? So for vectors, the first encounter of distance which you had was this Euclidean distance. So suppose I have x1 and x2 being the vector. What is the Euclidean distance or from 0, 0? Hello.
X1 square plus x2 square, square root of 4.
So that would be square root of x1 minus 0 square plus x2 minus 0 square, right? So this was the distance which you had initially, right? So this is essentially square root of x1 square plus x2 square. So this you called as your Euclidean distance. Let me make it capital, Euclidean distance. Or 2 norm. Right. Now there is one more concept of uh, in general P norm. P norm is essentially, suppose you have an n-dimensional vector x1 2 xn, you compute the pth root of this. So pth root of these components. So x1 to the power p, x2 to the power p, and so on. Right. So there are special cases of uh, norms which are one norm and infinity norm. So one norm is essentially the summation of absolute values of the components. Okay, and infinity norm is the maximum of all absolute values. So let's look at an example to understand. So let's say you have this vector which is 2 minus 3 5. Okay, so what is the one norm? One norm is the sum of all the absolute values. So it is 2 plus absolute value of minus 3 plus 5, right? Which is essentially 2 plus 3 plus 5 is 10. And infinity norm was the maximum value of the absolute value, which is 2, 3, and 5. The maximum of 2, 3, 5, which is 5. So this was the infinity norm. And similarly, for completeness sake, this is 2 norm, which is square root of 2 square plus 3 square plus 5 square. So you could compute that. So let's not waste time computing that. But these are the 3 norms. And in general, you could have a P norm. Let's say I have a 3 norm, let's say. So you could compute the cube root of the cubes. Now what happens if there are infinite elements in this vector? So in essence, you are computing the P norm, right? So you have this pth square root of summation of xi to the power p and I, right? Now what happens if there are infinite elements? So you could replace that summation with an integral, and you have this x of t to the power p dt from 0 to infinity, or whatever, like minus infinity to infinity, pth root, right? So it essentially becomes that if you have a vector of infinite dimensions, it is essentially a function, right? So at each index you have a value, so it is essentially a function. So in essence, this is an like extension for the norm definition. So if you look at these functions, which are nothing but infinite dimensional vectors, if you so will, this is essentially the 2 norm of the function, and this is the infinity norm of the function, which was the maximum of this, right? And there also exists a 1 norm. So if you look at the definitions of L infinity and L2, if I copy it over here, essentially we could remove the square root, because square root being finite implies the square is also finite. So this is finite and this is finite. So let's look at an example where this is happening, right? So you wanted that example. So let's say I have this function which is time dependent function, right? So f of t is equal to sine t. So let's compute the integrals. So integral of sine squared t dt. Is this square integrable? I mean, is this integral from 0 to infinity less than infinity? What is the answer?
I think yes.
No, sir.
No. Come again?
No, sir. No, sir. No. It is 1 plus cos.
Good. Good.
It would be area under the curve. So positively, it would be equal to infinity.
Yeah, it would be equal to infinity. Yeah. And what about L infinity?
Maximum of the value, so it would be 1.
So yeah, this was incorrect. So I realize
Okay.
it now. It should be maximum of this. Maximum of fx. So sine t, absolute value, maximum of it is 1, which is less than infinity. So it is L infinity, but it's not square integrable, right?
Yes, sir.
So you have one example which is L infinity but not L2, correct? Let's look at another example which is e to the power minus t. I'm looking at very simple functions. You could have like non-trivial cases as well, right? So let's look at whether it is L2. Is it? What is this value? If you have a paper and pen lying around, feel free to solve this.
It is finite, sir.
What would be the value?
1 by 2, sir.
Half. So let's check it. So the integral would be the integral would be e to the power minus 2t divided by minus 2. Right? Which is less than infinity. Hence, this function was L2. Now what about L infinity? The maximum value of
It's 1, sir.
which is 1, which is less than infinity. So this is less than, it is L infinity, right? Now, I want you to intuitively think, suppose there exists an arbitrary function. What does it mean to be L infinity in intuitive sense? L infinity implies that there exists a bound on this function. So ft being L infinity implies that there is a bound on this function. Whatever this function may be, this is always bounded. So L infinity implies boundedness, right? Now, so L infinity implies that the function is bounded. Now, what does it mean to be L2? L2 implies that the magnitude or this function, the square energy of this function is bounded. What do I mean by energy? So suppose there exists a function that it is not L2. So what does it mean to be like not L2? You can look at this function. So sine t, right? So there is this infinite number of crossings, and if you take the square of those, it is essentially this area under the curve is not being like finite. So there is an infinite area under the curve of the square function, right? So if there is infinite number of area in this square of this function, that implies that that function is not going to 0, because if the function which was bounded, let's say, if a bounded function is going down to 0, the area under the curve would approach a finite value as t tends to infinity. But since that the area under the curve of the square of the function doesn't approach a finite value, but rather it is unbounded, implies that there exists a constant or some kind of function such that there is a non-zero amount of area which is getting integrated. So L2 function and L infinity function. So if a function is both L2 and L infinity, that implies that the function dies down to 0. This is very intuitive. If you think about it a little bit, you can understand that if a function is bounded, so that is one condition. And the second condition is that if you take the square of that function and integrate it or find out the area under the curve, if that area is also bounded, then the function must die down to 0. Is this intuitive? Right? Intuitive enough, right? If there is any doubt, you can ask, because this is very important concept which would be used almost everywhere you do Lyapunov analysis. Right? So this is essentially a Barbalet's lemma. So let me give you a overarching higher level picture. So why do we do this? So why do we do this adaptive control? And why do we do this whole business of Lyapunov functions and all, right? So before going into that, let me ask, what is your background? So I would go around this meeting and ask what is the backgrounds of everyone. So how many of you are doing control theory? So please raise your hands. Doing control theory as part of your course curriculum. 1 and 2. Okay. And how many of you are into robotics? Let's say. You may lower your hands, and the second question may raise your hands. Into robotics or economics, let's say. Any other fields which involve dynamics or let's say you have a mechanical system, right? So control theory touches almost every aspect of life. So if you look at, let's say, robotics, so you have some manipulators. Let's say there is this kind of joints and structures over here. This system, you need to control this system. So you need to apply some voltages over here and some action over here, let's say, to move this object from here to here, let's say. So you need to apply a control effort. Another thing you can do is completely different from this. So you have, let's say, a stock market, right? So there is the price fluctuations of a commodity, let's say. You can model that price of that commodity as the state variable x, and you can compute the time derivative of that commodity price. You would have some function of x and time t. This is a very noisy estimate of that function, but this is a model nonetheless, right? Third thing, during COVID-19 times, right? So there was this whole talk about SIR models, or how many people would be infected, how many people would be susceptible, and accordingly, the governments made policies that affected that system. So you had, let's say, COVID-19 data. So you had the how many people are getting infected, how many people are unfortunately dying, and how many people are susceptible in this population. So you had these data points, right? So you had susceptible population, infected population, and deaths per population. So that could be considered as a state X. Now, in all of these cases, like different cases, stock market prediction or COVID-19 prediction, whatever be the values, right? Whatever be the system, you actually don't know the value of this function in the right-hand side. Because if you did, then you are literally God. So you actually don't know how these interactions or prices or whatever may change over time. So adaptive control, adaptive, and consequently learning based control as well. In the future, you may encounter this concept. Adaptive or learning based control is providing a way to control these uncertain systems which you don't know anything about in a judicious fashion. So this adaptive control or whatever, these are methods to tackle uncertainty in the systems. So you don't know about this stock market stock market, how this commodity would rise or fall, but you can obtain a nominal best case estimate, and based on that estimate, you could figure out how to apply your commodity trading strategies, right? So this adaptive control can be applied almost everywhere in the world. So including economic applications, everything, everywhere. So this is a very interesting topic, and the future applications could also include so-called neural network based controls and learning based controls as well. So all these approaches have been derived through this adaptive control. So this is a very exciting field of research as of now, and I'm sure that you would gain certain understanding of real world system dynamics, and you could apply that to your research or whatever you want to do. So this Lyapunov analysis plays a fundamental role in this adaptive control literature. So when you have this x dot is equal to some ax plus bu or something along those lines, where a is unknown or b is somewhat known or somewhat unknown, whatever. Here you would create a control u, which is u is equal to some k of x, which stabilizes or makes this system go to 0, even under the uncertainty of A and B matrices. So this is the beauty of adaptive control, that you don't know what your system is. You have some idea of the system, although, and you are still able to control that by learning that system online. So this is the overall higher level picture of why you want to do this course. So yeah. So are there any other questions? I could pause for some questions and we could then conclude that meeting.
Sir, can you tell the this definition of Barbalat's a little bit elaborated?
Okay, yeah, let me do that. Just give me 2 seconds, please. Yeah, hi, I'm back. So, Babelet's lemma. Now, Babelet's lemma, according to the definition, I'm not writing the entire definition, but I'm just giving a little bit of the intuition behind it. So, suppose there is a signal ET such that 3 conditions hold. So, the first is that ET is bounded. ET is bounded. Second, ET is square integrable. And third, ET is uniformly continuous. Uniformly continuous. This implies that E dot T is bounded. If that is the case, then ET goes to 0 as T goes to infinity. This is the Babelet's lemma. Now, let me give you an intuition of why this is. So, can you hear me? Yeah. So let me give you an intuition of why this is. So the first two conditions say that ET is bounded and ET is square integrable, or the area under the area under the curve of E square is bounded, right? Why the necessity of this third condition? Suppose there was this function Et and t, which had some discontinuities or breaks in the function. In other words, at this point, the time derivative of this function was infinity, because there is a sharp jump, right? So this sharp jump characterizes infinite time derivative. It is not continuous. It is continuous, it is not differentiable, or it's not uniformly continuous. Okay, so this condition, the third condition, precludes this kind of jumps in the function, right? So this must be smooth function on time. The signal must be smooth in nature. Now, if you look at the square of the function, so this was your time, this was E of t. So if you look at the square of the function, it would be like this. It would be like this. Sorry. And so on. Now the area of the integral, area of the area under the curve of this square, E square t, let's say this is not bounded, right? So in order to prove that this condition holds, if these conditions hold, then E of t dies down to 0. In order to prove that, let's say that the original
the sine function is not uh, L2 function, no, sir?
Yeah, sine function was not L2. Yeah, correct. So I'm showing that sine doesn't die down to 0. Exactly. So this was true, right? So sine function was bounded. The sine function always lies between -1 and 1, right? But it wasn't L2, right? So let's show that sine doesn't die down to 0 at infinity. We are essentially showing that. Okay. So if you look at the area under the curve of this, so this is not essentially dying down to 0. So there exists a periodic bump in this function, and the area is constantly increasing. So area is infinity as the time goes to infinity, right? So this function was bounded, and this function was uniformly continuous because there is no jumps in this function. So the only missing piece of the puzzle is this square integrable thing. So E square was the area under the curve of E square was infinity. So intuitively, if a function has to go to 0 at infinity, the area must converge to a finite value. Because there is a contradiction. If the area is infinite, this implies that the function must have a non-zero value of e square as time tends to infinity. Only then you can have infinite value of integral of e square, right? If this is 0, it is dying down to 0, then this would approach a finite value. So this is very intuitive way of saying that if these three conditions are satisfied, then E of t would die down to 0. It is a little bit hand wavy, but if you think about different examples, you can indeed see that if Et is going to 0 as t tends to infinity, then all of these conditions must be holding. So this is an if and only if condition. So this implies this and this implies this. Okay. Did that answer your question, Christopher?
Yes, sir. Yes, sir.
Okay. So we have time for one more question, I think, and then we would wrap up the meeting. So the rest of the questions you could post in that discussion forum which we have created, and we could answer that question. So there is one more TA along with me. His name is Pritesh Patel. So he and I would be handling your questions. And yeah, so is there any one more question which I could answer currently?
Hello.
Yeah, hi.
So my question is, I mean, it's not exactly mathematical, but I mean, what do we get out of it? I mean, so okay, so if we have a signal which satisfies the criteria of Barbalet's lemma, what will be the physical importance? I mean, I'm sure there is physical importance.
Yeah, absolutely. So in essence, you always want that your state or some part of the error, let's say. So if you have a regulation problem, so there are two kinds of problem in the control theory, right? So the people who are familiar with control theory may know this, that there is this concept of regulation problem. And there is this concept of tracking problems. In regulation problems, you have a state vector x, right? So the state being the variable of the ordinary differential equation. Now this state must approach 0. That is our objective. So let's see how. Wait a second. Yeah, we would have a recorded version of this. Actually, I would be uploading this on YouTube, and I would be sharing that link with you all. So yeah, there would be a recorded version. So there is a regulation problem and there is a tracking problem. So in regulation problem, let's say you have some state space representation. So let's say, let me give you an example to consider. So suppose you have a block like this, which is attached to a spring, and there is a friction acting on it. So this is the famous mass spring damper system. So this is the mass, this is the spring K, and this is the damper B, right? So the state in this system can be considered as the position and velocity of this block. So position or the displacement from this datum point over here is known as x, and the velocity is x dot or v, right? So the state variable is x comma v, which is your state variable. Now the differentiation d by dt of this is v, and it would be the expression is mx double dot plus bx dot plus kx is equal to f, where f is your control input, right? So if you look at this, it would be minus b by m into v minus k by m into x plus 0 comma 0 and f by m. So this is your state space representation. This is your state space representation. Right? So if you look at this, it is essentially a function of state capital X, where capital X is defined as this augmented state x comma v, comma u, which is f. So this is x dot is equal to f x comma u, right? Now the objective of this system is to apply a force such that this block goes down to 0, right? So suppose you want this to be the case. So essentially you want that x should go down to 0, and there can be another like control problem wherein you have this state x, right? And you want that the position must track some desired position and the velocity must track some desired velocity. So this is essentially that x should go to this capital X desired, where capital X desired is the augmentation of these two vectors, these two scalars. So this above problem is known as the regulation problem, and this problem is known as the tracking problem. So any problem in control theory can be framed as either one of these two, either tracking or regulation. Okay, now either x has to go to 0 or the error, which is defined as x minus xd, that must go to 0. So in either case, you want that the signals of interest must go down to 0. Now if you could show that state x is square integrable, state x is bounded, and state x is uniformly continuous, which means x dot is bounded, then you could prove definitively that xt would go down to 0 as t tends to infinity. So this Barbalet's lemma would be used repeatedly in this adaptive control course. So wherever you have these signals which you have to prove that they go down to 0, you would use this Barbalet. Sorry. Yeah. Hi. Did that answer your question?
Yeah. So basically, this Barber's lemma allows us to make an important point, basically make an important statement about the system without actually doing any of the computational effort to
Absolutely.
solve the system.
Absolutely. Absolutely.
So, to extend the example that you had given, that the RHS is something which is uncertain. There is probably a stochastic element to it. But if we are able to somehow confine our attention to systems which satisfy the criteria of Barbalet's lemma, then at the very least we can be assured of the fact that the state doesn't run away. If I'm
Yeah,
able to
exactly.
grasp that.
In fact, you can comment something better than runaway. It would die down to zero.
Yeah, it will die down to zero. Yeah, exactly. But so, just to think of a system that electrical people use quite frequently, a power electronic system, right? So their signals probably won't satisfy the third criteria, the
Uniform continuity, right?
yeah, uniform continuity. These switch systems, I presume, would be important in control.
Yeah.
But this won't be applicable.
Yeah, no, it won't.
So we are not looking at those kind of systems in this course. Right?
Switch systems, you could do that, and there are literature where you have adaptive control of switch systems. In fact, Pritesh Patel, who is another TA in this course, he's looking at these problems, but those are a little bit different. You have to consider like multiple Lyapunov functions, and you have to consider the switching in intervals. And switching is discontinuous, as you so it's not discontinuous per se, but non-differentiable switching. So yeah, during that you can't apply Barbour's lemma, but there are other techniques.
And finally, just a comment. I think probably we'll study that going further. This Barbour lemma does not give us any information about the rate at which the state goes to zero, right? It just makes a statement that it goes to zero, but
yeah.
will
So
it go down in an hour?
This is the difference between asymptotic stability and exponential stability. So asymptotic stability would essentially say that at time tends to infinity, it would be zero. But how it would go to zero, that asymptotic stability doesn't answer. But exponential stability says that the envelope of the system trajectories are converging at a rate of exponential.
Yeah, they're exponentially decaying, right? So in other words, they have a time constant, something like that. Exactly. They can be characterized in terms of a time constant. But exactly. There are time constants and time constants, right? 1 second time constant would be much faster than say a time constant of say 60 minutes.
Yeah.
Without exactly. Actually solving the system, as I presume we should be doing in these nonlinear systems.
Yeah.
Can we, I don't know, is there any mechanism by which we can make a rough and ready estimate of the rate at which systems are gonna die down? This state is gonna die down. A rough estimate, a probabilistic estimate or something.
You can find out the exact estimate. In fact, I can show you that. So here I had this example, right? So you were here in this example, right?
Yeah, where you compared it to a non-time invariant case, if I'm not mistaken.
Yeah, so this was that expression, and the v of xt was greater than x square.
Yeah. Okay, so we get it kind of like an upper bound, if I don't know if that's
no,
correct.
I can show you exactly what is the bound. So v of xt is upper bounded by x square, right? So I can sorry, not v dot, but v. Yeah, sorry, lower bounded. Lower bounded by x square, and v of v dot was upper bounded by minus x square, right? So if I subtract, like multiply -1 from both sides, it would be minus x square is less than minus v of x comma t. Right? So you can write that v dot is less than minus v of x. So suppose you have x dot is less than minus x, right? So you can say that x of t is less than x naught e to the power minus t. So this is the comparison lemma. In other words, in fact, if I have v dot less than some minus k into v, then I can write that v of t is less than some v naught, v of t naught e to the power minus kt. So this ratio between how much the v was and how negative that v dot is gives us the constant k in this expression. So it is an exponential result with time constant 1 by k. So as you increase k, the faster the system is. Right?
Yeah, yeah, that's clear. Thank you.
So even without computing the system dynamics, like integrating the system dynamics, you could have the Lyapunov function tell you how fast this is converging. So that's the beauty of it. Okay. So on that note, let's end the recording over here. And